Hello, hi everyone. Thanks for joining. We'll begin our class right now, and today it's going to be more practical than theoretical, and we are basically going to look at we're basically going to look at what how we implement a deep learning model. So I've added the code for that sample on this part, that is building and training deep neural networks. So the practical code is over here. If you open the Notion link that I shared with you, everything that we are going to feed for today is available there. So to start off, I'll start by showing you the tool that we are going to use, and that is Colab. So for you to use Colab, you'll have to be connected to your internet, and you can use any web browser to do this. That is Edge or Chrome. So you need to search collab.research.google.com, and you need to ensure that you are signed in to your Google account. So you open that, and then over here you'll have this welcome to Collab page, and then this pop-up over here. So for this pop-up that you are seeing over here, you can create a new notebook using the plus new notebook button, or you can open notebooks that you had created before. Okay, so that's what we can do. So what I'm going to do is I'm going to create a new notebook. So I'll click plus new notebook. And this will be the new IPYNB file that will be created for us. So it works similar to the Jupyter notebooks that you've been using, but this is an online version of it. So once you are here, there is this part at the top. So this is where you give your file a name. So I'll say this is the July 2024 deep learning intro notebook. So that will be the name for this notebook. And after I've given this notebook a name, I'll connect it. So you'll note that today I won't change this connection to a GPU connection because we are starting with the basics. That is fitting a model that can run on the CPU. That is a deep learning model that can run on the CPU. So let me split these into two so that we can code and copy the codes together all together. Okay, so I've zoomed in on the code, so you'll be able to see what I'm typing. So these are your code cells. So you can have code cells or you can have text cells. So I'll create a new text cell over here, and then I'll say this is the introduction to deep learning. And then add a few info about this notebook. So we will introduce deep learning in this section. So this is in this code along section. So you're supposed to copy what I'm typing and run it on your end as well. And once we have that, we can do a sample code. So print. So I'll just confirm Python is working. So I'll say my name. So that's my name. Then I'll print it out. So I'll print my name is, then we can have name. Yeah. So this is working. So this confirms that everything is working. So what I would like to ask you guys is to confirm if you are able to see the code that I am typing here. Should I reduce the size or should I increase the size, or is it okay? Is the size okay with you guys? Okay. Okay, great. So I'll give you 2 minutes to set up your notebook and make sure it's running, and then we can begin the actual coding. So for you, you can copy paste the code from the notes, but for me, I'll be typing them so that I can explain basically what I'm importing, what I'm typing for you to better understand what we are writing here. So 2 minutes at 8:13, we will start the code alone session. So I want everyone to fully set up their notebook and be ready for that. Hope you are done setting up your environment so we can begin. So the first and most important step is usually to import libraries that you need. So we will start by importing the basic libraries. So we will have NumPy. So NumPy as NP. Then we can import pandas as PD. We can have matplotlib and then Seaborn for any visualization that we are going to do. And so those are the basic libraries that we need. Then we can import sklearn libraries for data loading and pre-processing. Let me minimize this. So these are the 4 basic libraries that we need to import. And then now we can import the sklearn libraries that we need. So from sklearn dot datasets, we are going to import the breast cancer dataset because this is the dataset that we are going to use. So we are going to have load breast cancer. So this is a sample dataset. So we don't have to import any real world dataset for today. So we will use this sample dataset just for demonstration purposes. So you can see how these deep learning models are created. Then from there, we can import train test split for splitting our data into training and test set. Then we can import standard scaler for scaling our data. So this is not necessary. So not a must. And I'll explain why when we will be fitting our models. Then lastly, we can import our metrics. So from sklearn dot metrics, we import classification report and conversion matrix. So why are we importing classification report and conversion matrix? The kind of task that you are going to do is predicting the type of cancer that someone has or the type of breast cancer that an individual has. So this is a classification task. And if you go back to your machine learning class and refer to your notes, you'll see we usually use the classification report and the conversion matrix as metrics for classification. And a classification report, we have the recall and precision scores. And again, we have the F1 scores. So those are the metrics that we are going to use for these tasks. So those are the libraries that we need from sklearn. Then we are going to import Keras and TensorFlow libraries. So these are the deep learning models. So in brackets, the deep learning libraries. So those are the deep learning libraries that we are importing. So we will have from TensorFlow, import Keras. Then from TensorFlow.keras, we are going to import layers. So this is what we'll use to instantiate our layers. We are going to call callbacks. So callbacks is usually used for early stopping. So early stopping is where you stop your model from training. Uh, you just make your model stop training earlier, just in case it's not making any new progress. So we have that. I believe there is an error in this import. Let me import TensorFlow first. Import TensorFlow as TF. So the error is not gone. Okay, I'll check that later on and see if everything is working. Okay, then we are going to set a random seed for this work. So this random seed is there to make sure that the results that I'm getting are similar to yours. And no matter how many times you run this code, it means that your results will always be same to mine if you are using the same code that I am using. So we are going to have utils dot set underscore random seed, and then here we can use 42 as our random seed. So for the random seed, you can use any number. So it's not, it cannot be fixed on 42 alone. So you can use any number there. Then let me run this. I believe I might have an error, but I'll check it out. I don't know if this code has run. Let me copy it and paste it in a new cell. Yeah, so it's running. Okay. This is just an error appearing over here, but everything is working just fine. So maybe I can add a print over here and say something like libraries imported successfully. And we can run. So libraries have been imported successfully. So that's on the import part. So I believe you've copied this code and pasted it to your end. Or if you are typing it with me, you should be close to being done. So we have our libraries ready. So the next thing we need to do is we need to prepare the data set. Okay. So for the data set, what we are doing is we are loading this breast cancer data that we have over here. So we are going to say our data should be equal to load underscore breast cancer. Then we open brackets at the end. So this is an inbuilt way of loading data from sklearn. Then you can extract your X and Y. So your x should be equal to data. So what we are loading over here is actually something called a bunch file. So a bunch file is similar to a dictionary where you have key and value pairs. So where from our data, we have the key data, which has our features. And from data, we have the value target, which has our target variables. So we actually don't have to create a data frame from these directly. So that is our X and our Y. So if we check how our X looks like, you can see it's an array, and you can convert this array into a data frame by simply typing pd.dataframe, pd.dataframe, open brackets, you pass in your X, then comma, then column names should be equal to data.feature names. So we've got something that we've got a key that carries the feature names. And then we can check maybe the top three values for these. So pandas as, so these should be capital F. So these are the features that we have. So we've got the mean radius. So these are the breast features that we have from the scans. So we've got the mean radius, mean texture, mean perimeter, mean area, mean smoothness, mean compactness. All those features are there. And then we've got our value y over here, and y has all the predicted values. So as you can see from the definition that I've given you over here, zeros are supposed to represent the malignant cancer cases, and then one is supposed to represent the benign cancer cases. So we have that. So let's proceed. Now that we have our data set and it's in the form of arrays. So remember, I don't know if you are informed this, machine learning models usually work more fast with NumPy arrays compared to just passing the data frames as they are. So arrays are fast as compared to pandas data frame. So we will maintain the form of arrays that we have over here and fit the model as it is. But if you wanted to fit the model using a pandas data frame, you could do that as well. So the next thing we are going to do is we are going to create our train, validation, and test dataset. Okay, so this data does not have a test dataset. So this is just a single dataset. And we are going to split this data into three. So train, validation, and test dataset. Okay, so I'll add some explanation over here. So what is the validation data for? I believe you know what the training data is for and the test data, but you don't know what the validation data is supposed to do. So validation data is used by the model when back propagating to evaluate the model on data that it has not seen yet. So this helps the model. This helps the model know if it's learning from signals or noise. Okay. So once the model starts learning from noise, then early stopping is affected. Yeah. So that's what validation data is used for. So remember we imported callbacks up here, and I said that callbacks is used for early stopping. So what will maybe tell the model if it should stop training now or not is these callbacks in combination with the validation data. So the model will keep on evaluating itself, and it will check to see if the validation data is still dropping or if it has started rising. So if the validation accuracy starts to rise, then the model stops training because it will know that the model is learning from noise, and it should stop from there. So for the train test split code, I'll copy it directly because it's a little bit longer, and we will have that. So here we've got our X temporary data. We've got our X test. So X temporary data that we have over here, this is the data that we will use for training. And this is the data that we will split into training and validation set. Yes. Yes, Daniel. Yeah, it's okay. So let me explain this, and then I'll give you time to implement what I've implemented already. Hope that's okay. Yeah, so let me repeat the validation data, or let me summarize what we've done from the start. So here we've imported libraries that we need to use. And as I had mentioned earlier again, all the codes are available in the notes for reference. Okay, so we import libraries for basic data preprocessing and plotting. Then we import skline libraries. So we've imported the load breast cancer library for us to get the sample data from sklearn. Then train test split. We'll use this to split our data into training, validation, and test set. Then we have standard scaler for scaling our variables, and then we've got classification report and conversion matrix for model evaluation. Then here we import TensorFlow, as that's a library we need. Then we import Keras, and then from Keras we import layers, callbacks, and utils. So layers will allow us to create the perceptron that we had discussed yesterday. And we said for this perceptron, we have the input layer, the hidden layers, and the output layer. Then callbacks over here is there to stop the model from overfitting. Okay. So overfitting, this is when your model is learning from noise and not signal. And then utils is there just to set this random seed for replicability so that you can always get the same results as me. Then we've loaded the data. We said it's in a bunch file. That's our Y, this is our X, and they are all in the form of arrays. And now we were looking at this. So we are creating our X temporary data, which we will use to maybe split into training and validation data. So this is our train data. So if you are fitting a machine learning model, then you will basically just do this simple split. But since we are creating a deep learning model, we can specifically specify if this data can have a validation data set. So we have the creation of the train and test data set, and then we've got the split of the train data set into training and validation data. So I'll run this, then I'll give you maybe 3 minutes to have a look at what we've created so far, understand it, ask questions if you have any, and then we can proceed to the next part. So 3 minutes at 8:33, we will proceed. Just have a look at what we've done so far. If you have a question, you can ask. Okay, let's proceed. I hope you done with this part, and I hope you've understood the code concepts that we've created so far. So I'll skip the data scaling because, as I mentioned earlier, uh, data scaling is not necessary, and I'll explain why in this next part where we are building our network. So over here, we are creating, here we will create our model architecture. And this is where we instantiate the model. So we will say our model should be equal to keras dot sequential. You open brackets and then you open square brackets. So in here, this is where you are going to define everything about your model. So first of all, we have to create our input layer. So what is the input layer supposed to be for? So the input layer, this is where you are specifying the number of features that you'll have in your dataset. So if we come back here, let's first of all create that layer. So we will have layers dot input, and then over here we're going to specify the shape of the input. So this shape that we are defining over here is basically the number of X that we are to have. So if we go back to the presentation that I did yesterday, let's have a look at the drawing that I did. So if we scroll up, you can see we said we can have x1, x2 up to xn. So these are basically the inputs. And we are basically creating the input layer right now. So we will have layers.input, then shape should be equal to, you'll open brackets, then have your x train. So x train dot shape, then you pick the first number. Then you can close that bracket. So now you have your input layer. So let me now explain this further. So here in this data set, how many features do we have? So if we say, instead of dot head, we say something like dot shape. Let's see what we get. So we get 569 as the first index, and then 30 as the second index. So this is at index 0, this is at index 1. So this is what we are picking. So basically, our data has 30 features. So what we are passing in here is supposed to be 30. So we can get this directly from this output, or we can pass it directly over here to our model. Okay. So if we say shape, then we select one, you can see it returns 30. So our input shape over here is supposed to be 30. So this is our input layer, and this is how it looks on a graphical representation. So over here, this is our input layer. Okay, let's proceed. So we have our first layer. Next, what we are going to do is we are going to create these hidden layers that we have over here. And for the hidden layers, they can have as many units as you want. So this is unit 1, unit 2, unit 3. They can be any number. Okay. So I'll add a comma over there and then add our first hidden layer. And for our first hidden layer, I'll say layers dot dense. So kindly note this, we are using dense layers. Okay, so dense layers is these layers that I explained yesterday. So these are the layers that have an activation function, and they take in x multiplied by w plus the bias term. Then you add an activation function to it, and then you have that calculation happening over there. So that's basically what we call the dense layer. So we will have layers.dense, then we can have 512 units. Yeah. So I'm not using what is here, so 512 units. Then we can add an activation function. So yesterday we said ReLU is the best activation function that we can use. So that is hidden layer number one with an activation function. Then what we are going to do next is we are going to add, so I'll skip these batch normalization and dropout layers, and we are going to fit a second model with these two and see the difference that they bring when fitting these models. So we can have our second and last hidden layer. So we will have layers dot dense open brackets. So this will be half of 512, which is 256. Then activation should be equal to ReLU. So we will use a ReLU activation function. And lastly, we are going to create our output layer. And for the output layer, it will be layers.dense. And kindly note, for the output layer, you'll only have a single unit. Then activation, over here, we are going to use the sigmoid activation function. Remember yesterday, I informed you about the sigmoid and the softmax activation function. So over here, we are basically just using the sigmoid activation function. There is an issue. So I'll check my model summary just to confirm if everything is okay. So we'll have model.summary, open brackets. Perhaps you forgot to add a comma, so we should have a comma here, comma there. Yeah. Module carriers has no attribute input. So this is supposed to be capital I, not small I. Yeah, and that's our model summary. So I'll give you 2 minutes to have a look at this. So I'll re-explain what I've created over here again, and then you can have a look at it on your end as well. So what we are doing over here is we are instantiating our model. So remember, when you are fitting machine learning models, you instantiate your model and you've got the option for adding hyperparameters. So for deep learning, it's different. You have to create your input layer, you have to create your hidden layers, and you have to create your output layer. And in these layers, you have to pass in an activation function, and you have to specify the number of units that will be in each hidden layer. So for the first layer, the number of units will always be the number of features that you are using to train this model on. Then for hidden layers, you can use any number. So you can have 500, you can have 10, you can have 5, you can have basically any number. And then for the output layer, since this is a binary classification task, we are predicting if a cancer cell is malignant or benign. So we will only expect a single output. If it were a multi-class classification task, then let's say it had 10 different prediction values. Then for our last output layer over here, we would use 10 units because we would expect an output with 10 different probabilities. And we will not use the sigmoid activation function, we will use the softmax activation function. And we discussed this yesterday in class. So this is basically our model, and this is our model summary. Okay, so if we were to look at the input layer over here, so over here we will have x1 up to x30. If we were to look at the first hidden layer, here we will have 512 different circles. For the second hidden layer, we will have 256 different circles, and then for our output layer, we will have just this single circle that we have over here. That's the representation of our model. Yes, I see a question. So how many hidden layers are we supposed to create? I can see in this case you create two. So when fitting your model, you can start with any. You can create two or you can create 3, 4, or 5, depending on your use case. So at the end over here, I've added some points on maybe what should define how your model architecture should be. So we will discuss this as we are fitting the model. So first of all, I want you to understand how the model architecture is created. Yeah, so I'll give you 2 minutes to have a look at it on your end also. Make sure you understand it. And at 8:45, we are going to proceed on to the next part. Okay, let's proceed. So we've created our model, and from the model summary, this is what we have. So these are the different layers that we have, and you can see the layer type. So in this case, we only have dense layers. So we have hidden layer number 1. So you can see it's excluding the input layer. So we have hidden layer number 1. This is the shape, 512 units. And these are the total number of parameters that we have. So this is based off the mathematical equation that is at the backend. This is hidden layer number 2. And you can see it has 131 parameters. Then this is the last layer, which has only 257 parameters. These are the total parameters, and it shows you the total trainable parameters. So these are things that you won't know because these are calculations that are basically happening on your backend. So the model just tells you the total number of parameters, and you can use these parameters to guide you on which kind of hardware you are going to use to train this model, because the larger the number of parameters you have to fit, then the better the hardware you'll need and the longer the model will take to run. So yeah, let's begin. So for the model, uh, before fitting the model, we have to actually compile it. So we need to compile the model. And when compiling the model, this is where we tell it how it's supposed to train itself and how it's supposed to adjust its weights to better solve this task that it has at hand. So we'll have model.compile, and then we will pass in our optimizer. So yesterday we talked about the optimizer, and we said Adam optimizer is the best. And then we have to give it a loss function. Remember, yesterday we said this loss function is supposed to guide the model on how it's supposed to activate, how it's supposed to adjust its weights. So it's like an accuracy telling the model how well it's performing. So we will have loss being equal to binary cross entropy, because this is a binary classification task. and then we can add our evaluation metric. So for the model, it will be evaluated using accuracy. So when training, but once the model has been fully fitted, we will reevaluate it using the classification report from sklearn. So after we've instantiated our model, after we've compiled the model telling it what it needs to do and how it's supposed to adjust its weights to better do these tasks, we need to implement early stopping. Okay. So for early stopping, we will have early, let's say early stop being equal to callbacks dot early stopping. Then what we are going to monitor is we are going to monitor the validation loss, and then patience is supposed to be 10. So patience, I'll talk about patience when we are fitting the model. So when you are going to fit this model, you are going to define how many steps it's going to take. So initially, we can say that this model is supposed to run for, let's say, 100 different times. So in these 100 different times, so how many times should we monitor the model to say that it's making no further improvements? So over here, we specified that as 10. So that's supposed to be the meaning of that. And then restore best weights. So restore best weights is there to get the best accuracy score that was attained. And then we can say verbose should be equal to 1 for us to actually see those actual results that as the model is running. So this is our early stopping mechanism. So you can, what you are going to adjust here in early stopping is basically the patience and the restore best weights part over here. But I will recommend you leave these as default, leave these as default. Then for this, you can delete it. So here, you can use any loss. So you can use the training loss if you want your model to overfit. But over here, I'm basically using the validation loss, because for the validation loss, it will start rising if the model is learning from noise. But the training loss will keep on dropping even if it's learning from noise or signal. So I'll just show you a demo of that. I'll run that. So got keyword document metric, supposed to be metrics. Yeah. And now we've compiled our model. So after we've compiled our model, we need to fit it. So fit model. So this is how you fit your model. So you create a variable called history that we will carry all the data that will be extracted from the fitting process. And then we can fit our model. So we'll have model.fit. We will pass in our X-train, our Y-train dataset. So remember, this is how we define that. So this was our X-train, Y-train, and then we have our validation dataset being equal to xval and yval. So we define that up here. So you have xval and yval. So these are used for validation. Then what we are passing over here is something called epochs. So epochs is the number of different trainings that are going to happen for this model. So here we are saying that this model should fit 100 different times. And then batch size here is 32. So what is batch size? So batch size is there to maybe tell the model, this is the amount of data that you are supposed to see in each and every run. Okay. So if you've got a powerful CPU or GPU, you can increase this batch size because it's basically dependent on the space that you have and the number of hyperparameters that you have. And if you've got a smaller GPU or CPU, you can reduce this batch size and increase the number of fits. Then we implement callbacks. So we pass in the early stopping variable that we had earlier created up there. And then we say verbose should be equal to 1. for us to actually see the results of this model. So I'll run that. So here you can see we have epoch 1 up to 100. And for each epoch, you can see we've got the accuracy, the loss. So it's actually running quite fast. Uh, let's wait for it to run. So you can see it only ran for 47 different fits, and early stopping got into the way. So why did early stopping come in? So you can see for this model that we were running, let's have a look at the validation loss. So from these initial fits that we were having, it started going down from 0.51585060. It went to 0.42, 0.40, the best, 0.37, 35, 32, 31, 28, 24, 23. It started now going up. Okay. And once this accuracy started going up from this point. So you can see we had 0.2235, and then it spiked up to 0.440, and then it kept on going up. So this model, what it did is it went back to these steps that we were fitting, and notice that epoch 37 had the lowest validation accuracy. And if we confirm, you can see we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got 10 new different fits that were done to check and monitor the model and see if this validation loss would have gone lower to a number lower than 0.2355. So it means it never went lower, so we had to retain the best validation accuracy. So that's how you look at this data. So I wouldn't recommend you look at it here. So you can change over here verbose to be equal to 0 to remove those epochs that you are seeing over here and just get these part. So it's saying it did 17 different epochs, and early stopping was done over here at epoch number 17. And then it restored the model weights at 7 over here. So once we have this, how can we monitor this model and see if it did the work that we wanted it to do? So let me rerun this again and see if we can get a better number over here. So we had 13, 11. So I actually know what I'm doing wrong over here. So I'm rerunning this model. So it will always reduce the number of epochs that we have over here, not unless I restart the runtime. So let me restart it on my end. So restart session. And then runtime, I'm supposed to run all cells again. Okay, so we have 47 different epochs. So this is better. Before I proceed on to that part that I was to show you. So we've removed the logs using verbose being equal to 0. So let me repeat the explanation of these two parts so that you can further understand how they work and how they are different from machine learning. So here for machine learning, we usually instantiate our model by saying model should be equal to linear regression, for example. So it's the same case for deep learning models. So we say models should be equal to keras.sequential. Then we specify what should be in our layers. So I've explained this here. So the first layer is always the input layer. And for the number of units is supposed to be the total number of features that you have in your data. Then the hidden layers are usually there with hidden units with random number of units, so you can have any, but simply make sure that first hidden layer has more units as compared to the second hidden layers, but you can experiment with different numbers. Then the output layer always has a single unit if it's regression or binary classification. If it's multi-class classification, you can have more units over here, but use a different activation function. Another thing I forgot to tell you is for regression, we usually don't have an activation function here at the end. So we just need the prediction that comes from the last hidden layer. Then you can print out your model summary. Then before you can fit your model, you need to tell your model what it's supposed to do to make it improve. So you compile the model and you add an optimizer. So we talked of the optimizer yesterday in the theory class, and you know what the optimizer is supposed to do. And you add the loss function. So the loss function is just there to tell the model if it's doing the work correctly or if it's making any improvements. And then metric is there to monitor the model, just a different value. So to monitor and see if the model is doing the intended work. Then we implement early stopping. So for early stopping, you can specify what you want to evaluate. So here we are monitoring the validation loss. We can monitor the training loss if we wanted to. Then we specify the patients. So after how many successful trainings with no improvement should we stop training? So here we are saying after 10 different fits with no further improvement, just stop and restore the best accuracy that we had from the model. So here we say that should be equal to true. Then verbose should be equal to 1. So you know what verbose is supposed to do. So it's supposed to log the results out for you. Then we come to the model fitting part now. So we create a variable called history, and this will store all the different data that we will get from the fit. So we will have model.fit. We pass in our X-train and Y-train dataset, and then we pass into the validation data variable our X-val and Y-val dataset. Then we specify the epochs. So these are the different number of fits that we are going to have. So in this case, we are going to have 100 different fits, and then we specify our batch size. So batch size over here is 32. So it means that this is the number of samples of data that the model is going to see on each and every fit. And I said that this batch size is mainly dependent on your hardware capabilities. Okay. And you'll get to see this when we are fitting models that are on big dataset. And then you add callbacks for early stopping. And lastly, verbose to either display or not display the outputs. So just a minute, have a look at that, and then we can proceed. Okay, anyone with a question on that? Anyone with a question? Okay, if you've got no questions, then let's proceed. So we've specified verbose over here to be equal to 0. So how can we actually check and monitor to confirm if our those how can we check those logs in a better way? So we can do plots. So we can plot the accuracy of the model. So here we will have plt dot plot. Then we will have history. Then we pick the accuracy. Then label should be accuracy. So this is the training accuracy actually. And then you can have plt.plot again, history.history, and then you can have the validation accuracy plotted. And then we can have plt.title. We can add a title to this plot. This is the accuracy curve. And then we can plot the loss values as well. So we'll have plt.plot, history.history. We will have the laws and validation laws. We can add the title, legend, and then we can show the actual plot. So these are the plots, and you can see the fits as they are happening. So let me maximize this so that you are able to see what we are having over here. So you can see, let's look at the loss. This is the training loss, and this in orange is the validation loss. You can see the training loss starts by going down. It goes down, and here at epoch, let's say this is close to 37, it starts going up again. So this means that the best training parameters that we could have had for this model are at point 37. So this means that the model has stopped training over here. And this can be seen on the accuracy curve as well. So the accuracy starts by going up with minor changes still going up. But once we get to, let's say, epoch number 35, that is training number 35, you can see the loss drops significantly, which means that the accuracy drops significantly, which means that the model is now learning from noise rather than learning from signals that it should be learning from. So let's summarize this by having a look at the last part, that is the classification report. So over here, we will have our YPRED being equal to, then we are going to have model.predict. Then we are going to pass in our X test. So we are predicting on this. So here, what we are going to do is we are going to predict on values that are greater than. So we are checking for values that are greater than 0.5. So if a value is greater than 0.5, it's supposed to be converted to a 1, or else it's left at 0. So we will have as type int, then we are going to have int 32, then we unravel out the outputs. Then we print out the classification report. So the classification report will have all the details that we will need. We can run that. So this is our model accuracy. So it's not that much great. You can see it has an accuracy of 0.92 and an F1 score of 0.89 for class 0 and an F1 score of 1 for class an F1 score of 0.94 for class 1. So that's what we have for the model. Before we finalize the class, so this is something this is self-explanatory. It's similar to what you've been doing in machine learning. So before we end the class, there is something I had promised to add. So kindly note this down. So this model, the base model that we've created, has an accuracy of 0.92. So I'll paste that down there. So how can we improve this model? Remember, I had informed you earlier that we can ignore the data scaling over here. So how does it impact our model? So we can add data scaling directly to our model architecture. And how do we do that? So for our first hidden layer, what we do is we just type in layers dot batch normalization, and this will normalize your data. So it's similar to scalar dot it's similar to standard scalar where you're scaling your data. And then we've got this thing called dropout. So dropout, what does it mean? Let me explain what dropout means over here. Uh, just a minute. So this is a representation of dropout. So let's say we've got this first unit, this second unit, and this is fit number 1. So we've got our first hidden layer over here. So it means that this will be the input for that, 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 and that. So for the next hidden layer, let's say it only has 2 values. So for dropout. So if we say our dropout is equivalent to 0.5, so dropout ranges between 0 and 1. So it is in terms of percentage. So if we say dropout is equivalent to 0.5, then this will be an input for this, and this will be an input for that, maybe. This will be an input for that, and this will be an input for that. So you can note that for these hidden layers, we are not getting an input from this unit to this unit, and we are not getting an input from this unit to this unit. So it has been split 50-50. So that's what dropout is all about. And what is the use of dropout? So dropout is there to remove any patterns that, so it's there to remove any bad patterns that the model is running. So let's add dropout and batch normalization to our layers and see how it improves the model. So we add layers.batch normalization and layers.dropout. So I'll run that again. I'll compile the model. I'll feed the model. So I'll share this code with you and you'll have a look at the batch normalization part. So we are fitting the model. You can see it's now taking a little bit longer than before to run this model. And then we can plot the training and validation accuracy. So you can see with batch normalization and dropout, the curves are actually a little bit smoother. So it has eliminated the volatility that we had in the training and validation loss. So you can see the validation loss is a little bit smooth and the training loss is even more smoother. So if we look at the classification report to see if there was an improvement, you can see our model has improved from having an accuracy of 0.92 to having an accuracy of 0.96. So that is basically the use of batch normalization and dropout. So if you wanted to further improve this model, so how will you do it? So the first way to do this is make these layers wider or make them deeper. So how do you make them deeper? So to make them deeper, you increase this number of units that you have over here. So you can increase this to 1000 and so. And how do you make them wider? So you add even more hidden layers. So I can say here, layers.dense, we add that 128 units. We add layers.dense, we add one with 64 units. So this is a wider hidden, this is a wider model. So let's run this and see if it actually improves the accuracy of our model. So we had 0.96. Let's see if we are going to get a better accuracy or a lower accuracy. So it has stopped at T-Box 29. This is the curve. This is the loss curve. This is the accuracy. So we get 0.89 as our accuracy. So it has actually given us even worse results. So we can go up here and remove those new layers that we added. And I can maintain what we had earlier. So that's our layer, which has an accuracy of 0.96. Yeah, so that's basically it for today and for the introduction to neural networks. So you can see, you've seen how we create the neural networks, how we inst how we instantiate the models, how we compile the models, how we fit the models, and how we plot their accuracy curves to monitor if they are doing the work that we want them to do or not. So I'll share this notebook with you. Let me make it public. The link done. Let me basically add it to the notes so it's easier for you to access them there. So class notebook link. Yeah. Yeah, so that's the notebook link for everything that we've done for today. So you can open that link and have a look at the code that I've created. Yeah, so that should be it for today. As I've mentioned, you've seen how we can instantiate the model, compile the model, implement early stopping, feed the model, and create these curves. So as a bonus, before we end the class, what I'm going to do, let me maximize this. So I'll move fast on this part. So what we are going to do is we are going to fit a logistic regression model and compare to the results of our model. So this is just a quick thing that I'm going to do. As I am doing this, you can ask questions if you have any. So here we're going to have from sklearn dot linear underscore model import logistic regression. Then what we do is we instantiate our model. So we'll have log model being equal to logistic regression. Then we'll have log model dot fit. We fit on the X train and Y train. Then our Y pred should be equal to log model dot predict on the X test. Then we print the classification report. Let's run that and see what we get. So you can see from our logistic regression model, we get an accuracy of 0.93, which is actually a little bit lower than our initial model. So let me fix this. So it's supposed to be max eta to fix the error that we are having. Let's have 1,000. 1,000 is not working. 10,000. Yeah. So if we increase the number of iterations, we get a score close to what we have in our deep learning model. So they are actually giving us similar results. Let me do a comparison. So this is 0.95, 9497, 95, 9497. So actually similar results. So yeah, when it comes to tabular data, you can stick to the normal machine learning models. But with what I've shown you over here, this is just an example of how you can create the models. So that should be it for today. Let's have a look at what we are going to discuss next week. So next week, we are going to look at regularization and optimization techniques. So how can you optimize these model further to give you better results and to solve cases that the normal machine learning model cannot? Yeah, so that should be it for today. Anyone with a question? Yes, Daniel? Yes. Yeah. Yeah, data preprocessing is applied on the deep learning models as well. So the reason as to why I skipped data preprocessing today is because you can see I had to explain the deep learning model in detail, how it works and its architecture. If I was to start by doing data preprocessing, then I believe we would have not completed this today. But for upcoming tasks, we will be doing data preprocessing uh, just for you to see how we preprocess our data and make them ready for our models. Yeah, hope I've answered you. Okay, great. Anyone else with a question? Question or a concern? Okay, if you have no questions, then I'll stop the class recording.